Hello and very good afternoon to you all. I'm Matt Taylor from Fluid Handling International, and I'm very excited to introduce to you the Rapid and Reliable Pipeline Leak Detection webinar, brought to you by global specialist KROHNE, a world-leading manufacturer and supplier of solutions in industrial process instrumentation. Demand for pipeline leak detection and location systems is increasing rapidly. Presenter Daniel Voigt will lead you through an interesting presentation discussing the fundamental principle of the ERTTM method for rapid and reliable leak detection, showcasing system potential by way of a sample case study taken from the chemical industry. Daniel is product manager for Pipe Patrol, the leak detection system for KROHNE Oil and Gas. His responsibilities include strategic product development of Pipe Patrol, as well as conceptual design and planning of leak detection solutions, considering both client and regulatory requirements. So, without further ado, I'm going to hand you over to Daniel.
Thank you, Matt. Well, welcome everybody to our webinar. And I would say we dive straight away into our presentation, Rapid and Reliable Pipeline Leak Detection. My name is Daniel Vogt, and I'm working now for over 12 years in the field of pipeline leak detection and localization, the last 10 years together with KROHNE. I think my responsibilities have already been explained by Matt, so we will skip this slide and go straight to our overview. So the topics we are going to cover in this presentation are a short introduction, where we show reasons, for example, and why leak detection systems are applied. We will also cover the regulatory framework related to leak detection systems. And in the second topic, we will explore what kind of leak detection systems are available, how modern leak detection systems detect leaks. The third topic will cover a real-world application, and we will wrap up this webinar with a short conclusion about what we have discussed before. So, in general, where do we find leak detection systems?
Crude oil and ethylene. Just check my speakers.
Excuse me. Okay, so leak detection systems we find typically on transport pipelines. Two examples are given in the pictures on this sheet. On the left picture, we see an ethylene pipeline network. An ethylene pipeline network where producers and consumers of ethylene are connected. So these pipeline networks, they do not only deliver the smallest CO2 footprint, they are also environmental friendly compared to other alternatives, like, for example, trucks or railways. And they also provide the most secure transportation method. They are very cost effective, and they can be found not only in the chemical industry, but also, as seen on the right side, in crude oil transportation. On the right side, we see a crude oil pipeline starting on the top left from the gathering fields, transporting the product to the different storage locations with several pump stations in between over a distance of several hundred miles. Those two pipelines seen on these pictures are very well known to us because nowadays both pipelines are monitored by KROHNE's leak detection system, Pipe Patrol. Okay, in many parts of the world, the major industrial sites like gathering sites, refineries, chemical plants, production sites, they are all connected by pipelines. And as we all know, the transported materials, crude oil, refined products, natural gas, ethylene, hydrogen, maybe even carbon monoxide, are potentially hazardous to human and environment. So this increases the requirements regarding safety dramatically, especially if pipelines run through urban centers, like, for example, Houston or Edmonton. On this slide, we want to show some major incidents which happened with pipeline leaks in the past years. One example, in July 2004, an explosion caused by a leak in a gas pipeline injured 132 people and killed 24. This leak was existing for 14 days before the gas exploded. Another example from July 2010 is a 6-foot break in a pipeline which resulted in the largest oil spill, the largest inland oil spill, and one of the costliest spills in the US history. In Germany, in March 2012, we found a pipeline leak where around 1 million liters of kerosene leaked out into the environment because the leak remained undetected for a period of several weeks. All these catastrophes shown on this slide could have been avoided with a modern leak detection system. In many countries on this world, it's also necessary to install a leak detection system because of official requirements we find. One example is the TRFL, the Technical Rules for Pipelines we find in Germany, which is known as the most stringent regulation regarding to pipelines worldwide. Another one is the API Recommended Practice 1130, which covers computational pipeline monitoring for liquids. There are other requirements available, like the API 1175, the API 1149, the Code for Federal Regulation, or the Canadian Standard Association Z662. To give you an example about how requirements are defined, we will just have a closer look at the TRFL and the API 1130. So TRFL from Germany has been issued in 2017. So this is the last issue for TRFL, and it requires a pipeline operator to install 2 continuously operating technical processes installed on your pipeline that can detect leaks in steady state. So these technical processes need to be based on different physical variables. In addition, you need a process for detecting leaks during transient operation. This is, for example, a pump start, a pump emergency shutdown, change of set point, change of product in your pipeline. You need a process that can detect leaks during standstill conditions. So when your pump is not in operation. A process that detects gradual leaks. So gradual leaks are those small leaks like small corrosion pinhole leaks, which only leak with a few liters per hour. And in addition, you need a process for leak localization. So this requirement covers leak detection from the operational point of view. In other words, it requires you to have a leak detection system which works during all different pipeline operating conditions. It's interesting to know that in Germany, all those requirements are verified by an independent third-party authority. So if you want to operate a leak detection system and if you install a leak detection system, all these requirements are verified and certified. Otherwise, you are not allowed to operate your pipeline anymore. So we now come to the second topic. Which modern leak detection systems or which leak detection systems are there available on the market to detect leaks? And if we look into the API 1130, API 1130 gives us the possibility to categorize leak detection systems. On the one hand, we find the non-continuously working systems. So non-continuously working systems may be, for example, the inspection by helicopter, smart pigging with an intelligent tool, or even tracking dogs. We, however, want to focus on the continuously working systems, so systems which monitor your pipeline 24 hours a day, 365 days a year. And those systems, again, can be divided into the so-called external methods and into the internal methods. External methods are called external methods because they require an external, additional leak detection sensor to detect a leak. This might be, for example, a fiber optic cable. Fiber optic leak detection systems are very famous today. This can also be an acoustic system using a microphone, listening for the sound of a leak. We find sensor hoses or video monitoring systems. In contradiction, there are what is called internal leak detection methods. Internal leak detection methods use the existing instrumentation. So the instrumentation which is already available on your pipeline to operate your pipeline, like pressure, like flow, temperature. Based on this instrumentation, those methods try to decide if there is a leak in your pipeline or if there is no leak in your pipeline. Very simple method is what is called the balancing method. Balancing method try to balance the injection flow into your pipeline with the delivery flow, so they rely on flow meters. We also find statistical methods. Statistical methods try to achieve a specific or a higher confidence into their decision for a leak before they give an alarm. We also find the RTTM system, which is the abbreviation for real-time transient model-based systems. So they calculate and consider the change of line pack in your pipeline and use it to balance, to create the overall mass balance. And we find what is called the extended real-time transient model-based systems. They are the latest development in this group, and they combine those several internal methods into one unique approach and into one advanced system. In December 2012, PHMSA, the US Department of Transportation for Pipelines and Hazardous Materials Safety Administration, issued a leak detection study. In this study, they actually give a recommendation which equals the German regulation in its content. What they actually say is that there is no reason why several different internal leak detection methods should not be implemented at the same time. In fact, a basic engineering robustness principle calls for at least two methods that rely on entirely separate physical principles. As an example, the extended real-time transient model system, trademarked by KROHNE, uses a real-time transient model in conjunction with several other API 1130 technologies. So this approach is not only a basic engineering robustness principle, but it's also available and industrial proven with the KROHNE ERTTM method. So how does an ERTTM system work? As I already said before, in traditional balancing, we compare the mass flow of the pipeline injection to the delivery, to the mass flow of the pipeline delivery. And it's really important to say that we are talking about mass flow, because there is the physical principle of mass conversion, but there is no principle of volume conservation, which means a lot of flow meters are volumetric devices. In this case, the flow needs to be calculated to standard conditions or to mass flow. On this picture, we use mass flow devices, and we see on the left side a trend of 24 hours from a pipeline, the injection flow in blue and the delivery flow in green. So according to the principle of mass balance, the injection flow should equal the mass flow. So if I compare both, the result should be 0. However, it can be seen that for a period of several hours, the balance is not 0, even if there is no leak in the pipeline. This effect is caused by the compressibility of the product, which means the line pack or the inventory of the pipeline changes. Yes, it's a typical effect we find for gas pipelines where no storage tanks are available, so the pipeline is used as a tank and the product is stored in the pipeline. So at this time, the pressure in the pipeline will increase as the flow increases at the injection, but the delivery flow, which is controlled because it feeds some process behind the control valve, does not change. And if we now just balance the injection and delivery flow, we run into a problem. So balancing systems try to avoid these false alarms by using a high alarm limit. So they use a very high threshold, or they extend their detection time. A lot of statistical systems do this as well. So if the pipeline flow becomes dynamic because of inventory change, detection time extends a lot. So both these effects affect the sensitivity of a leak detection system. And with modern methods, this is not required anymore. With Pipe Patrol ERTTM, we have a two-stage system. Pipe Patrol ERTTM is based on the principle of statistical pattern recognition. So I have to emphasize this right from the beginning. Even if it uses a real-time transient model, it is not a simulation and it is not a real-time transient model system. It's an extended real-time transient model system. And it's based on the principle of statistical pattern recognition. It's true in the first stage, it uses a real-time transient model, or in our presentations, we call this a virtual pipeline. So our marketing calls this a virtual pipeline, but this is only used to create specific leak patterns. And in the second stage, stage 2, which is the E in the name of our system, extended, we add signature analysis. Signature analysis is a statistical process which detects the leaks and avoids the false alarms. So we are now going a little bit more into detail to explain how this method works. And we start with the first stage, the real-time transient model. In KROHNE system, this fully dynamic real-time process model calculates the leak-free target values. On the picture below, you see your pipeline. Now, on the computer, we build the real-time transient model or the virtual pipeline. We use the geometry of the real pipeline, the elevation profile, the material quality, so the wall thickness, the length of the pipeline, properties of the product, and the thermodynamic equation of state of the product. And all this together, we throw this together, and we end up with a set of partial differential equations, the conservation of mass, momentum, and energy. And those equations, they describe the flow everywhere inside your pipeline, the pressure everywhere inside your pipeline, the density inside your pipeline. So they describe the dynamic behavior of this physical characteristics, or they describe the hydraulic behavior of your pipeline. And partial differential equations can be solved using boundary conditions. And in this example, we use the online measurements, pressure and temperature at pipeline injection and pressure and temperature at pipeline at delivery to calculate the flow in your pipeline. Simplified said, it's like a huge orifice plate. But in fact, it's a little bit more complicated. And because it's based on the conservation equations, the system calculates in real time how the flow should be in the pipeline if there is no leak. As I said, it calculates the leak-free target values. This model is based on the method of characteristics, which is today considered as the most accurate for one-dimensional flow in pipelines. So now we have calculated in real time how the flow should be in your pipeline if there is no leak. Now we compare this flow, this calculated flow, with the measured flow, because you remember we have not used the flow meters for our system yet. The calculations have been based on pressure and temperature yet. So on this picture, we see what we call the pattern generation. We see the same example from before, but this time, in addition to the calculated flow, we added from the measured flow, we added the calculated flow. So we still have the measured injection flow in blue, and in a pink color, we added the calculated flow from the model. And we have done the same in green and red for the delivery flow. So we subtract those flows now, and we receive what we call the filtered decision values. Filtered decision values. We call it filtered decision values because, as you can see, the operational dynamic, so the transient behavior is nearly completely gone from these values. There are still some residuals left, but most of the operational dynamic is gone. However, we at KROHNE, we understand that a real-time transient model can never achieve a 100% accurate simulation or representation of your pipeline. So there will be deviations, as seen, leftovers, but also there may be deviations due to other effects like temperature effects along your pipeline you cannot take into consideration because you have 120 miles of pipeline between your measurements. Other effects because instrumentation may drift. So there are a lot of things which cause deviations between calculated values and measured values. And instead of comparing our filtered decision values against the threshold, we feed it into our second stage. And this second stage is called signature analysis. Signature analysis monitors the decision values for the signature of a leak. So whenever there is a deviation in a decision value, signature analysis will compare this deviation with a database, and only if this deviation matches the signature of a real leak, pattern recognition will give an alarm. Otherwise, it may give a drift warning or it will discard the deviation because it's not a leak signature. With pattern recognition, we created a very robust system with minimum false alarms per year, and depending on the application, customers have gone for over 10 years without false alarms. What I have just explained is what we call the vertical combination of methods. So we combined a real-time transient model, creating flow decision values with leak signature analysis. However, KROHNE system also provides a horizontal combination of methods. So in addition to this flow residuals, or what could also be called an extended real-time transient model or compensated line balance, we can provide a negative pressure wave method or pressure flow drop methods. We also have, for robustness reasons, traditional balancing methods, compensated or uncompensated, and also hydrostatic pressure tests. So all these methods can be applied to your application, to your pipeline, but of course they must not be applied. So this gives us the chance to optimize our system individually to the customer's environment. So we don't need to install all of these methods on a 2-mile refined product pipeline, where maybe 1 or 2 methods are sufficient. However, using multiple methods improves the performance significantly. It also allows to fulfill the requirements, local requirements like TRFL, but also recommendations like API 1175 for primary and complementary leak detection system or alternative leak detection system. As the system uses a real-time transient model and a pattern recognition method next to the detection of a leak, it can also provide additional information. This includes, but is not limited to, the localization of leaks, hydraulic profiles, including the maximum allowed operational head calculations, line pack calculations, product and batch tracking in multi-product applications or crude oil applications. The system provides life cycle monitoring and efficiency calculations. Also, the system monitors the vapor pressure and can handle slackline conditions along the pipeline. And it also provides an overpressure monitoring along your pipeline. So after explaining the theory behind KROHNE's extended real-time transient model-based systems, we would like to show a real-world application and describe the results which have been achieved with the system. So in the real world, one of the questions is, how do I implement this leak detection system into my environment? And there are many, if not hundreds or thousands ways of implementing a leak detection system, but in a general scheme, we start on the bottom of this picture. We have a pipeline. This pipeline may be existing. It can also be a new build pipeline. And on this pipeline, you need, as we already learned before, for an internal leak detection system, you will need instrumentation. At every injection and delivery, we need flow, pressure, and temperature. Ideally, this instrumentation comes from KROHNE. In this case, we can guarantee specific system performance. However, the system, of course, it does also work with any other kind of instrumentation, any other brand, but also it's not limited to mass flow meters, so you can use any kind of meters. We have implemented the system with Coriolis meters, ultrasonic meters, clamp-on flow meters, orifice plates, turbine meters, venturi tubes, so whatever you can think about. This data needs to be transferred into your control room. Usually this is done using an existing SCADA system. If no SCADA system or no data acquisition is available, KROHNE can provide PiPatrol data acquisition units, which are specific RTUs which use a data format which is tailored to our system. In any case, the data should be available at some point in a control room where the leak detection server resides. The leak detection server can be a piece of hardware which is delivered by KROHNE. It can also be a piece of hardware which is delivered by the customer because he may have some IT regulations, but it could also be nowadays a virtual environment. So on this leak detection server, we install the software, which is literally a Microsoft Windows software, and we install our interface software. And this interface software uses a plug-in driver interface. So traditional, the communication to the SCADA system would be OPC, but we have a plug-in driver interface. We can talk to any SCADA system with Modbus, serial, RTU communication, TCP/IP communication, Profibus, whatever is available. So the system can be integrated with any SCADA system available. We have done integrations with ABB, Allen Bradley, Siemens, Amazon, so whatever you can think about. And we can talk to the SCADA system or to a PLC directly, whatever is required to implement the system. So the system now receives the data from the pipeline instrumentation, does its calculation, and then based on the integration, it can play back the results into the SCADA system, but it also provides an HMI, a leak detection HMI. This HMI is a web-based HMI, so it's also hosted on the leak detection server, and it can be opened and monitored from any leak detection workstation. The leak detection server can be redundant, so we can have redundant communication, we can have a redundant system, and we can have as many workstations as you like. The HMI is also capable, because it's HTML5, so it's capable of mobile devices, so it's compatible to iOS, to your iPhone, to your iPad, or you can open it with your Android phone. As said, the system can be implemented to greenfield projects, it can be implemented to existing systems, and whatever is required, the flexibility is there. In this application now, we want to show how the system behaves during a leak test on a 7-mile, 6-inch gas pipeline. So on this pipeline, leak tests have been conducted. A spontaneous leak or several spontaneous leaks were created. 165 feet from the inlet, and the leak flow went into a flare. So the gas was flared. And 3 leak tests were done actually, which is based on the nominal flow reference conditions at this is 141,243 standard cubic feet per hour, or 4,000 standard cubic meters per hour. So based on this reference conditions, this is a 2.5% leak, a 0.5% leak, and a 1% leak. So these were the 3 leak trials which were carried out. And if we look at the flow during the course of this day, during this day, you can see that there is no chance to find the leak trials in this data. So on the top graph, we can see again the injection and delivery flow of this pipeline. And as it's a gas pipeline, it's used for storage and it's operated in high dynamic conditions. It's operated in high dynamic conditions. So even if we create the volume balance, and I have to point out again, so this is standard volume. This is not the volume from the flow meter. This is already volume calculated to standard conditions. So if you look at the bottom graph, the volume balance, even in this volume balance, it's impossible to see the 3 leak trials. Even if we zoom into the trial period, it's very, very difficult to find the leaks. So if you have not seen this chart before, you will not find it. But I can tell you those 3 leaks are there, and this is actually what we want to show. So the first leak, the 2.5% leak, is the 2.5% leak is right here. And yes, you could have guessed it, but the small leak, the 0.5% leak and the 1% leak, there is no chance to see it in the flow values and also not in the balance. The situation changes a little bit if we add the model calculated values. So now we do this for the injection flow. We see the measured flow in blue in the top graph and the calculated flow in red. And we now plot them in the same trend. We can see there is some kind of deviation for the first leak trial, but even for the second and the third leak trial, it becomes very difficult to see this leak. The filtered decision value now makes detection of leaks already a little bit better. So we can very clearly see the 2.5% leak here, but for the 0.5% it becomes difficult, and for the 1% leak, it could be possible to locate it here in this data. But for a system just using a threshold, a static threshold, or even using averaging over a specific time period, these leaks would not be visible. And this is why KROHNE uses what we call, or what is generally known as pattern recognition. This pattern recognition is the main intellectual property of KROHNE. So for your information, about 2/3 of our program code are in this pattern recognition, where the model approximately uses 1/3 of the program code. And here you can see very clearly on the bottom graph how good pattern recognition works out the leak pattern from the original decision data. So we can see the 2.5% leak very clearly. You can see this change, and you can see this change in the 0.5% leak, and you can also see this change in the 1% leak. So for every application we install, we do what we call an optimization phase. And during this optimization phase, we try to find the optimal performance for this application, for the ERTTM system. So it's somehow the sweet spot where the system works best. So no false alarm with highest sensitivity. We achieve an application-specific performance plot, which gives us the leak detection threshold, so the smallest detectable leak rate, in relation to the required detection time. And now, when we have this blue line, we can make the decision which parameter we use for the system to operate. All the parameters chosen on the left side, for example, if we choose the detection time of 300 seconds and the smallest detectable leak rate of 0.5%, we can see we are on the left of the blue line. This would result in false alarms for this specific application. So this is why we choose parameters in the what is called the safe zone on the right side of this performance plot. So for this pipeline, we have chosen a minimum detectable leak rate of 1% with a detection time of 5 minutes. And all this distance to the blue line is additional safety from false positives. And as mentioned before, this pipeline has been in operation for over 10 years without any false alarming. So let's wrap up what we have seen before. ERTTM methods are superior to other methods we find on the market. Independent institutions have conducted tests of different leak detection methods, and the results prove, so they have tested the extended real-time transient model-based systems against traditional real-time transient model systems and against statistical systems, and it can be seen that this extended real-time transient model-based system has the same reliability as statistical systems, but it's much more robust than the real-time transient model-based systems, and it provides a much higher sensitivity because detection time is up to 4 times faster, even for small leaks. And this makes ERTTM systems the ideal system for theft detection. PiPatrol ERTTM nowadays is installed on over 350 applications worldwide. We are represented with the system in more than 20 countries, and we minimize your false alarms. With KROHNE PiPatrol ERTTM, we can guarantee you continuous and robust monitoring during all pipeline operating conditions with the help and use of the classic instrumentations and multiple API 1130 methods. In many cases, ERTTM systems are already in use and they have been certified by an independent third-party audit. In fact, every system we operate in Germany, this must be approximately 50, are independently certified. We provide optimization and continuous support of KROHNE during the lifetime of the system. Yes, keep in mind, KROHNE is a big company compared to other vendors. We are like 100 times bigger, so you can be sure that we still exist the next 50 years. and we provide you the support and guidance to fulfill and exceed the legal requirements which are you can find in your country. If you are interested in our system, please visit our webpage where we offer you or we provide you more information. We also have a fantastic e-learning available related to pipeline leak detection systems and additional documents like the brochure of our system, application reports, scientific documents. So everything is available on the webpage. Of course, we are also happy if you contact us directly. So I would like to thank you for your attention